Okay, we have a falling parachutist from a plane and it's a velocity time graph. Okay, right, first question. We have to work out the acceleration of the parachutist at t equals 6. Right, time is 6, so that's here. So we have to work out the acceleration at that point there. Right, on a velocity time graph, the gradient at that point will give you the acceleration, because gradient is rate of change. So the rate of change of the velocity is acceleration. Okay, so we're going to work out the gradient at that point there. Grab your ruler and draw the tangent to this curve at that point. A nice long line so that it cuts the y-axis here. So it's going to be something like that. Okay? So get that on the paper, on the graph. The longer the line, the better. It's good if you can get it to cut the y-axis, because we'll work at that point there. We'll work with from time t equals 0. And it's easy to work out whatever the value is when it actually cuts the axis. Don't go using a little triangle here. Use a big one. And then choose some sensible point up here somewhere that corresponds to a nice time value, 10 maybe, and a good velocity value. Okay, so part A, the gradient is rise over run. So you've chosen your 2 points. The rise is that distance there, and the run is that distance there. Okay, so you have to work out the rise to start off with. Well, the rise will be whatever that value is. I'm just going to call that V2. And I'm going to call whatever this value is V1. So the rise is V2 minus V1. That minus that. Okay, it's gone up that distance. And the run, well, it's gone from here, so that's going to be T1, which is 0 if you've got it cutting the y-axis, to T2, there. So the run is going to be T2 minus T1. Okay, now I've drawn this by hand, and it's not going to be the same as the values you actually read from your question paper. So I deliberately haven't given a value for that, okay? Or that, or that. But if you've done this reasonably accurately, according to the mark scheme, when you've put in your values, you should come out, stick it in the calculator, you should come out with a value somewhere between 3 and 4. Let's call it 3.5. Now, the units, if the velocity is meters per second, units of acceleration is meters per second squared. That's just another way of writing meters per second squared. Doesn't matter which one you use. Okay, next bit. Distance fallen in 12 seconds. Okay, I think I'll change colour for this. So we have to estimate, so that's an estimate, the distance fallen in the first 12 seconds. So from 0 to 12. And we're told to use 3 strips of equal width. Right. You need to know that on a velocity time graph, the distance fallen is the area under the graph. Okay? So up to 12 seconds here, okay, we're going to calculate this area here. Okay, so remember now, on a velocity time graph, the distance covered is the area under the graph. Okay, I'll write that down. Distance equals area. Area under graph. Okay, that's for a velocity time graph. It doesn't work on a distance time graph. Okay, distance is area on a velocity time graph. Okay, now we're told to use 3 strips of equal width. That means we have to divide up the time distance, that's 12 seconds, into 3 strips. Well, 12 divided by 3 is 4. So one of the strips is going to start there. For another 4, another one's going to start there, and the third one's going to be there. So here are our 3 strips. But how high do they go? Well, the first one has got a width of 4. Well, they've all got a width of 4. If we took it all the way up to there and across, okay, so to there, then and we worked out the area of that rectangle, it'd be a pretty bad estimate, right? Because we only want this area here. So what you do is take it up to the midpoint. Take the strip up to that point there, okay, and go across from wherever the midpoint of the strip hits the graph, and work out the area of that box there. Okay, because 2 is the midpoint, hits the graph there, so go across there. Because if we work out the area of this box, it's roughly, this is only an estimate, half the area of that larger box if you went all the way to 4. Because this line here is roughly half, cutting this big rectangle in half. So if you work out the area of this one, which is roughly half the height of that one, the area of that box will be roughly equal to the area we want. Okay? So it's going to be that times that, which is 4 times, it's just happened to be 20 the way I've drawn it. It's going to be different on yours because this is hand drawn. Okay, same thing here. Okay, the midpoint between 4 and 8 is 6. So go up, I've already done it. It hits there. So the top of our strip is going to be there. It goes down there and there. Okay, so that's our second strip. And again, if you work out the area of that strip, it's going to be roughly equal to the area under the graph from here to here, because the area of that bit is roughly equal to the area of that bit. So by calculating the area of this strip, we're including this area, but we're discounting that area. So they kind of cancel out and you get roughly the right area for this thing here. Okay, so that's our second strip. Our third strip, 10, go up, it hits about there. So our third strip is going to be, goes down to 8. There. Okay, so that's how you're meant to divide it up into strips. So now we can do the area calculation. The area is, it's just the area of these 3 strips. So the first one, area is width times height. Width is 4 seconds. Height on mine is 20. Okay, I'm going to use the values that just happen to have fallen on mine. Again, it's hand drawn. yours is going to be different on the graph paper. Slightly different somewhere. So, plus this second box, width from 4 to 8 is 4. Width times height, and the height of this is roughly 47. Okay, and again, the area of this third strip is 8 to 12 again. The width is 4 seconds. Width times height. Height is roughly 56 meters per second. Okay, stick that in a calculator, work it out, and that will give you the area. Okay, now I've written down what I think the values are from the actual graph on your question sheet, and the values that you should be reading off using this method are, oh, 20 is the same. Ha! Genius. Nailed it. 4 times 20, so that's the same. 46, not bad. Okay? Again, just to reiterate, on your graph paper, that value should be 46. And 53, oh come on, that's pretty close. Not bad at all. Okay, so just to stress why, make sure you understand why I'm changing these numbers. It's because I've hand drawn this and it's not perfectly accurate. I'm changing these to the numbers that you should find on your actual question sheet. Okay, that's 46 and that's 53. Right, stick that in the calculator or do it in your head if you can. And it comes out as 476. 476 watt distance. Units, meters. Which is what you'd expect. You're doing this times this, meters per second times seconds, you're left with meters. Okay, it's an estimate. You don't have to get exactly 476. Okay, some number around that value. You might read off a slightly different value here, the way on the y-axis from when you go across. I think these are the correct values, but it's okay if you get a slightly different value looking at your question sheet. It's the technique that counts. Okay, you should get a number somewhere in that region. But the important thing to take away from this is how to divide this up into strips properly. And also, you've got to know that on a velocity time graph, the distance under the graph is given by the area. Sorry, the distance is given by the area under the graph on a velocity time graph.